Welcome to this coding problem walkthrough. Today, we'll be tackling problem number 433, titled Minimum Genetic Mutation. In this problem, we'll explore how to transform a genetic sequence from a starting point to an ending point using the minimum number of valid mutations. Stick around as we break down the problem, analyze approaches, and derive an efficient solution. In this problem, you are tasked with finding the minimum number of genetic mutations needed to transform a starting sequence into a target sequence. These sequences are represented as strings of length 8, where each character can be one of a C, G, or T. These characters represent genetic bases. Along with the starting and target sequences, you are given a bank of valid genetic mutations. A mutation is defined as a single character change in the genetic sequence, and for a mutation to be valid, the resulting sequence must exist in the given bank. The goal is to determine the minimum number of such mutations required to transform the start sequence into the end sequence. If the transformation isn't possible, the output should be -1. The input includes the start and end strings, along with a list of bank strings, and the output is an integer representing the minimum number of steps needed, or -1 if no solution exists. Let's consider a concrete example to understand the problem better. Suppose the start sequence is AACCGGTT, the end sequence is AACCGGTA, and the bank contains only one sequence, AACCGGTA. To transform the start sequence into the end sequence, we can change the last character T to a, resulting in the sequence AACCGGTA. This mutation is valid because the resulting sequence is present in the bank. Since the transformation is completed in just one step, the output for this example is 1. Here's another example to explore a slightly more complex case. The start sequence is AACCGGTT, the end sequence is AACCGGTA, and the bank contains three sequences, AACCGGTA, AACCGCTA, and AACCGGTA. First, we can change the last T in the start sequence to A, forming AACCGGTA, which is valid since it's in the bank. Next, we change the second C to A, resulting in AACCGGTA, which is also valid because it's in the bank. This transformation requires 2 steps in total, so the output is 2. Now, let's look at an example requiring 3 mutations. The start sequence is AACCC, the end sequence is AACCCCC, and the bank contains AACCCC, AACCCC, and AACCCCC. First, we mutate the fourth A to C, resulting in AACCCC, which is valid since it's in the bank. Next, we mutate the third A to C, forming AACCCCC, which is also in the bank. Finally, we mutate the second A to C, giving us the target sequence ACCCCCC. Since 3 valid mutations are needed, the output is 3. There are a few important edge cases to keep in mind. If the start sequence is already the same as the end sequence, no mutations are needed, so the result is 0. If the end sequence is not present in the bank, it is impossible to complete the transformation, and the output should be -1. Similarly, if the bank is empty, no valid transformations can occur, so the output is also -1. Finally, if no valid sequence of mutations exists to transform the start sequence into the end sequence, even if the end sequence is in the bank, the result should still be -1. These constraints ensure the problem is well defined and guide us in handling edge cases appropriately. To tackle this problem, we first need to understand its structure. The task involves transforming a starting genetic sequence into a target sequence using a series of valid mutations. Each mutation changes exactly one character in the genetic string, and the resulting sequence must exist in a predefined list called the bank. Conceptually, this can be modeled as a graph where each sequence is a node, and an edge exists between 2 nodes if their sequences differ by just one character. The goal is to find the shortest path in this graph from the start sequence to the end sequence, using only the nodes provided in the bank as intermediates. This framing of the problem helps us identify efficient strategies to compute the solution. One approach we could consider is an exhaustive brute force search. Here, we would generate all possible one-character mutations for the current sequence, check each mutation against the bank to ensure it's valid, and then recursively explore further mutations from there. While this approach ensures that every possible path is explored, it is extremely inefficient. With a sequence length of 8 and 4 possible characters at each position, the number of potential mutations grows exponentially, resulting in a time complexity of 4 to the power of n. Additionally, the recursive nature of this approach requires a space complexity of O(n) for the call stack. This large branching factor makes brute force impractical for this problem, as it would take far too long to compute. A more efficient strategy is to use breadth-first search, or BFS. In this approach, we treat the genetic sequences as nodes in a graph and explore them level by level. Starting with the initial sequence, we generate all possible one-character mutations. For each valid mutation, that is, one that exists in the bank, we add it to a queue for further exploration and remove it from the bank to prevent revisiting. This process continues until we reach the target sequence or exhaust all possibilities. BFS guarantees the shortest path because it explores all mutations at the current level before moving deeper. The time complexity of this approach is O(n*(m), where n is the size of the bank and m is the sequence length, as each sequence is checked once and generating mutations takes O(m). Space complexity is O(n plus m) to account for the queue and visited nodes. This approach is both efficient and straightforward, making it a strong candidate for solving the problem. Another variation to consider is bidirectional BFS, where we simultaneously perform BFS from both the start and end sequences, meeting somewhere in the middle. By reducing the depth of each search, this method effectively cuts the search space in half, which can lead to faster results in practice. The time complexity remains O(n*(m), similar to standard BFS, but with smaller constant factors due to the reduced search space. Space complexity is also O(n plus m), but implementing bidirectional BFS adds complexity to the code, as it requires managing two queues and merging paths. Ultimately, while bidirectional BFS is theoretically faster, its added implementation overhead isn't justified for this problem given the relatively small constraints. That's why we opt for the simpler optimized BFS approach. This method is not only easier to implement but also ensures we achieve the shortest path efficiently without unnecessary complexity. In summary, BFS strikes the perfect balance between simplicity and efficiency for solving this problem. It models the genetic sequences as nodes in an unweighted graph and finds the shortest path in a straightforward and reliable manner. While brute force is impractical due to its exponential growth, and bidirectional BFS introduces unnecessary complexity, standard BFS is both effective and appropriate given the constraints. By carefully managing the bank to avoid revisiting nodes, we minimize redundant computations and ensure optimal performance. This makes BFS the ideal choice for transforming the start sequence to the end sequence using the given bank of valid mutations. The goal of this problem is to determine the minimum number of mutations needed to transform a starting genetic sequence into a target sequence, given a list of valid intermediate sequences. Each mutation changes exactly one character in the sequence, and the result must be a valid sequence found in the provided bank. This can be thought of as a shortest path problem on an implicit graph. Each sequence represents a node, and an edge exists between two sequences if they differ by exactly one character and the resulting sequence is valid according to the bank. To solve this, we use breadth-first search, or BFS, since it is well suited for finding the shortest path in an unweighted graph, which is exactly what this problem models. To begin solving the problem, the first step is input validation. If the target sequence is not in the bank, the transformation is impossible, so we return -1 immediately. Similarly, if the start sequence is the same as the target, no mutations are needed, and we return 0. Next, we pre-process the bank by converting it into a set. This allows us to perform O(1) lookups, making it efficient to check whether a sequence is valid. Then, we initialize the BFS process. A queue is used to manage the traversal, where each entry is a tuple consisting of the current sequence and the number of mutations so far. The queue starts with the given starting sequence and a mutation count of 0. Additionally, we use a visited set to keep track of sequences we have already processed to avoid redundant work and infinite loops. Now for the BFS traversal process. While the queue is not empty, we dequeue the front element, which gives us the current sequence and the mutation count. If the current sequence matches the target sequence, we return the mutation count because we have reached the goal. Otherwise, we iterate over each character position in the current sequence. For each position, we try substituting the character with each of the 4 possible genetic characters, A, C, G, and T. This generates a new sequence, which we check against the bank and the visited set. If the new sequence is valid and hasn't been visited, we add it to the queue with an increment mutation count and mark it as visited. If the queue is exhausted and we haven't reached the target sequence, we return -1, indicating that the transformation is not possible. Using BFS ensures that when we do find the target sequence, it is through the shortest path, which corresponds to the minimum number of mutations. The data structures used in this approach are essential for its efficiency. The queue is the backbone of BFS and ensures that we explore all nodes at the current mutation depth before moving to the next level. Each queue entry contains the current sequence and the mutation count, and its FIFO behavior guarantees that we process sequences in the correct order. The bank is stored as a set to allow O1 lookups, making it quick to validate whether a sequence is valid. Finally, the visited set helps us track sequences we've already processed. This prevents revisiting the same sequence, avoiding redundant computations and infinite loops, which is crucial for optimizing the algorithm's performance. Several key insights help us understand why this approach is effective. First, BFS guarantees optimality because it explores all sequences at the current mutation depth before moving deeper, meaning the first time we reach the target sequence, it is through the shortest path. Second, converting the bank to a set significantly increases efficiency by reducing the time required to check if a sequence is valid. Third, the use of a visited set ensures minimal redundancy, preventing cycles and unnecessary computations. Finally, it's important to handle edge cases appropriately, such as returning 0 when the start and target sequences are the same, or -1 when the target is not in the bank or when no valid mutation path exists between the start and the target. Now let's analyze the complexity of the algorithm. The time complexity depends on the length of the sequences, denoted as n, and the size of the bank, denoted as m. For each sequence, we generate all possible mutations by changing each of its n characters to one of 4 possibilities, which takes O and *4 time. Since BFS processes each sequence at most once, we perform this operation for up to m sequences, giving a total time complexity of O m*n. For space complexity, the queue can hold up to m sequences in the worst case, and the visited set also stores up to m sequences, resulting in a total space complexity of O m. Together, the algorithm is well optimized for the problem's constraints. Let's walk through an example to see the algorithm in action. Suppose the start sequence is AACCGGTT, the target sequence is AACGGTA, and the bank contains AACCGGTA, AACGCTA, and AACGGTA. We initialize the queue with the start sequence and a mutation count of 0, and the visited set contains only the start sequence. First, we dequeue AACCGGTT with 0 mutations. Among its possible mutations, AACCGGTA is valid, so we enqueue it with a mutation count of 1. Next, we dequeue AACCGGTA with 1 mutation. Its valid mutation AACGGTA matches the target sequence, so we enqueue it with a mutation count of 2. Finally, we dequeue AACGGTA with 2 mutations, and since it matches the target, we return 2 as the minimum number of mutations required. This example demonstrates how BFS efficiently finds the shortest path, ensuring the solution is correct and optimal. To solve the minimum genetic mutation problem, we start by importing the D class from the collections module, as we'll use a breadth-first search approach. First, we define our function minMutation, which takes 3 arguments: start, the initial gene sequence, end, the target gene sequence, and bank, a list of valid gene sequences. The first thing we check is whether the end sequence exists in the bank. If it doesn't, there's no way to transform the start sequence into the end sequence, so we return -1 immediately. Next, we define the valid gene characters A, C, G, and T, which are the only options we can use for mutations. To optimize lookups, we convert the bank list into a set, which allows us to check membership in O1 time. Then, we initialize a queue for our BFS, starting with the start sequence and a mutation count of 0. The BFS loop begins by dequeuing the first element, giving us the current sequence and the number of mutations so far. If the current sequence matches the end sequence, we return the mutation count as the result. Otherwise, we attempt mutations by iterating over each position in the current sequence. For each position in the sequence, we iterate over the 4 valid gene characters A, C, G, and T. If the character at the current position is the same as the one we're trying to mutate to, we skip that iteration since there's no change. Otherwise, we create a new sequence by replacing the character at the current position with the new gene character. If this newly mutated sequence exists in the bank_set, it means it's a valid mutation. In that case, we add the mutated sequence to the BFS queue along with the updated mutation count, which is increment by 1. To avoid revisiting the same sequence, we also remove it from the bank_set. This ensures that our algorithm remains efficient and doesn't cycle through already processed sequences. Finally, if we exit the BFS loop without ever reaching the end sequence, it means a valid transformation path doesn't exist, and we return -1 as the result. Here, we start with the Java implementation of the minimum genetic mutation problem. First, we define the method min_mutation that takes the starting gene sequence, the target gene sequence, and the available gene bank as inputs. To ensure the target gene sequence can be reached, we convert the gene bank into a set and check if it contains the end sequence. If not, we return -1, as the transformation would be impossible. Next, we define the valid gene characters, which are a C, G, and T. Then, we initialize a breadth-first search, or BFS, queue with the starting sequence and a mutation count of 0. The queue will help us explore all possible mutations layer by layer. As we proceed, we use a while loop to process the queue until it's empty. For each sequence in the queue, we extract the current gene and the associated mutation count. If the current gene matches the target sequence, we return the mutation count, as we've successfully transformed the start sequence into the end sequence. Now, we explore how mutations are generated and validated. For each position in the current gene sequence, we attempt to mutate it by replacing the current character with each of the valid gene characters. If the character remains unchanged, we skip that iteration. For valid mutations, we generate a new sequence by combining the sections of the current gene before and after the mutated position along with the new character. If this new sequence exists in the gene bank, it means it's a valid transformation. We add this mutated sequence to the BFS queue with an increment mutation count, effectively marking it as the next step in our transformation process. To avoid revisiting the same sequence, we immediately remove it from the gene bank set. This ensures we don't waste time processing sequences we've already explored. If the BFS completes without finding the target sequence in the queue, we conclude that it's not possible to reach the target and return -1. Finally, we define the helper class pair, which is used to store each gene sequence along with the number of mutations it took to reach that sequence. This allows us to keep track of both the state of the sequence and the progress of the transformation. The class contains two fields, gene, which holds the current gene sequence, and mutations, which tracks the number of mutations performed up to that point. The constructor initializes these fields when a new pair object is created. By organizing the gene sequence and its mutation count into a single object, the BFS queue remains well-structured and manageable, simplifying the overall implementation of the algorithm. Here, we start with example 1, where the initial genetic sequence is AACCGGTT and the target sequence is AACCGGTA. The available mutations are provided in the bank, which is just AACCGGTA. First, we convert the bank into a set for quick lookups, resulting in bank_set equals AACCGGTA. Then, we initialize a BFS queue with the start sequence and a mutation count of 0, so the queue becomes DEQ AACCGGTT 0. During the first BFS iteration, we dequeue AACCGGTT and explore all possible single-character mutations by systematically replacing each position with a C, G, or T. Most of these mutations, such as CACT, ACAGT, and ACGAT, are not present in the bank, so they are ignored. However, when mutating the last character, we generate AACCGGTA, which matches an entry in our bank set. We add this sequence to the queue with an increment mutation count of 1, updating the queue to DEQ AACCGGTA 1 and removing AACCGGTA from the bank set. Now, the bank set is empty, and we move to the next step in our BFS process. In the second BFS iteration, we dequeue AACCGGTA with its mutation count of 1. At this point, we check if the current sequence matches the target sequence. Since AACCGGTA is indeed the end sequence, we return the mutation count of 1 as the result. This means it takes exactly one mutation to transform AACCGGTT into AACCGGTA using the given bank. With this, the first example concludes, and the final output for this example is 1. Moving on to example 2, we now have a slightly more complex scenario where the start sequence is AACCGGTT, the target sequence is AACGGTA, and the bank consists of 3 sequences, AACCGGTA, ACCGCTA, ACGGTA. For this example, we begin by initializing the BFS process. The bank is converted into a set, resulting in bank_set equals AACCGGTA, ACCGCTA, ACGGTA, and the queue starts with deq ACCGGTT 0. In the first BFS iteration, we dequeue AACCGGTT with a mutation count of 0 and explore mutations. When mutating the last position, we generate AACCGGTA, which is found in the bank set. We add AACCGGTA to the queue with a mutation count of 1, updating the queue to deq AACCGGTA 1, and remove AACCGGTA from the bank set. The updated bank set now contains AACCGCTA and AACGGTA. In the second BFS iteration, we dequeue AACCGGTA with a mutation count of 1. This time, mutating the third character produces AACGGTA, which is in the bank set. We add AACGGTA to the queue with a mutation count of 2, updating the queue to deq AACGGTA 2, and remove AACGGTA from the bank set. The remaining bank set now consists of AACCGCTA. In the third BFS iteration, we dequeue AACGGTA with a mutation count of 2. Here, we check if the current sequence matches the target sequence. Since AACGGTA is indeed the end sequence, we return the mutation count of 2 as the result. This indicates that it takes 2 mutations to transform AACCGGTT into AACGGTA using the given bank. The final output for this example is 2. Now, we move to example 3, where the start sequence is AACCC, the target sequence is AACCCCC, and the bank contains 3 sequences, AACCCC, AACCCC, AACCCC. In this example, we begin by converting the bank into a set, resulting in bank_set equals AACCCC, 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 and initializing the BFS queue with deq AACCC 0. During the first BFS iteration, we dequeue AACCC with a mutation count of 0 and explore mutations. When mutating the fourth character, we generate AACCCC, which is in the bank set. We add it to the queue with a mutation count of 1, updating the queue to deq AACCC 1, and remove AACCCC from the bank set. The updated bank set now contains AACCCC and AACCCC. In the second BFS iteration, we dequeue AACCC with a mutation count of 1. Mutating the third character produces AACCCC, which is in the bank set. We add AACCCC to the queue with a mutation count of 2, updating the queue to deq AACCC 2, and remove AACCCC from the bank set. The remaining bank set now contains only AACCCC. In the third BFS iteration, we dequeue AACCCC with a mutation count of 2. When mutating the second character, we generate AACCCC, which is in the bank set. We add AACCCC to the queue with a mutation count of 3, updating the queue to deq AACCCC 3, and remove AACCCC from the bank set. The bank set is now empty. In the fourth BFS iteration, we dequeue AACCCC with a mutation count of 3. At this point, we check if the current sequence matches the target sequence. Since AACCCC is indeed the end sequence, we return the mutation count of 3 as the result. This means it takes 3 mutations to transform AAACCC into AACCCC using the given bank. The final output for this example is 3. To analyze the time complexity of this problem, we begin by focusing on the breadth-first search approach. The BFS loop processes each valid sequence in the bank at most once. If the bank contains n sequences, the outer loop runs O(n) times in the worst case. Now, within the BFS, we generate all possible single-character mutations for the current sequence. Since each sequence has a fixed length m of 8, and we iterate through 4 possible gene characters for each position, this results in 4*m potential mutations per sequence. While only valid mutations in the bank are processed further, we consider the worst-case scenario where all 4*m mutations are valid. This gives us a time complexity of O(m) for generating mutations for one sequence. Together, these steps form the basis for understanding the overall complexity of the BFS approach. Now, combining the components of the BFS, the total time complexity can be derived. For n sequences in the bank, the BFS processes all n nodes, and for each node, mutation generation requires O(m) time. This results in an overall time complexity of O(n*(m). Next, considering the space complexity, the bank_set is created to allow constant time lookups for valid mutations, which requires O(n) space where n is the size of the bank. Additionally, the BFS queue stores sequences and their mutation counts. In the worst case, the queue holds all n sequences, each requiring O(m) space due to the sequence length. This makes the space requirement for the queue O(n*(m). Finally, other variables used during BFS, such as those for tracking the current sequence and mutations, require O(m) space in total. These components together define the memory usage of our approach. When we sum up the dominant factors, the total space complexity of the algorithm is O(n*(m) due to the bank_set in the BFS queue. Now, let's discuss how this complexity changes across different scenarios. In the best case, the start sequence directly mutates to the end sequence in one step. Here, BFS processes just one sequence, leading to a minimal complexity of O(1) for both time and space. In the average case, BFS explores a subset of the bank before finding the end sequence, and the time and space complexity are proportional to the size of the subset. However, the average complexity remains approximately O(n*(m). In the worst case, BFS exhaustively explores all sequences in the bank, either to determine that the end sequence is unreachable or to process it as the last node. In this scenario, the time and space complexity reach their maximum of O(n*(m). To understand why the BFS approach is more efficient, let's compare it with a naive recursive solution. The naive approach would generate all possible mutations for each sequence without leveraging BFS. This results in an exponential time complexity of O(4 to the power of m), due to the branching factor of 4 at each of the m positions in a sequence. This is clearly impractical for larger sequence lengths. In contrast, the optimized BFS approach eliminates redundant work by only exploring valid mutations present in the bank and using a visited set to ensure each sequence is processed at most once. These optimizations reduce the overall complexity to O(n*(m), making the BFS approach significantly faster and more scalable for this problem. To mathematically verify the big O complexity, consider that BFS processes each sequence in the bank at most once, contributing O(n) to the time complexity. For each sequence, we generate mutations by iterating over m positions and testing for possible gene characters per position, resulting in O(m) operations. This leads to a total time complexity of O(n*(m). Similarly, the space complexity is determined by the BFS queue and bank_set. The queue stores up to n sequences, each requiring O(m) space, and the bank_set also requires O(n) storage. Combined, the space complexity becomes O(n*(m). In conclusion, the BFS approach is both time efficient and space efficient compared to the naive solution, offering a robust and practical strategy for solving the minimum genetic mutation problem. Now let's discuss some common mistakes to avoid when solving the minimum genetic mutation problem. First, one frequent issue is not validating the bank. This happens when you assume the bank always contains valid and unique sequences. The problem with this is that duplicates or invalid sequences in the bank can cause unexpected behavior, such as revisiting sequences unnecessarily or leading to runtime errors. Next, another mistake is skipping edge cases. For instance, scenarios where the start sequence is the same as the end sequence, or the end sequence is not in the bank at all, are often overlooked. Failing to handle these properly can result in incorrect answers, like returning an invalid mutation count. Lastly, there's the issue of inefficient graph traversal. Some may use a depth-first search, or DFS, instead of a breadth-first search, or BFS. This is problematic because DFS explores deeper paths first and doesn't guarantee the shortest path, while BFS is specifically designed to find the minimum mutation count in this type of unweighted graph problem. Continuing on, another common mistake is hard-coding mutations. This involves manually checking for mutations, such as by writing out specific character replacements, instead of dynamically generating them. This approach can easily lead to errors and doesn't scale well for longer sequences or more complex mutation rules. Another pitfall is failing to track visited nodes during the BFS traversal. If you don't maintain a visited set, the algorithm may revisit nodes that have already been processed, leading to infinite loops or redundant calculations, which drastically increases time complexity. Shifting gears to interview insights, this problem is a textbook example of the shortest path in an unweighted graph. Here, genetic sequences act as the nodes, and valid mutations form the edges between them. To solve this efficiently, BFS is the optimal approach, as it guarantees the shortest path. Represent sequences as graph nodes, dynamically generate mutations to check for edges, and use a set for the bank to ensure O1 lookups. Additionally, keeping a visited set helps avoid revisiting nodes. Aim for an overall complexity of O n asterisk m, where n is the number of sequences in the bank and m is the length of each sequence. Lastly, during interviews, it's important to clearly explain why BFS is superior to DFS in this context and how you're dynamically generating mutations instead of hardcoding them. To expand your understanding, there are several related problems on LeetCode that follow similar patterns. For example, LeetCode 127, word ladder, is another shortest path problem that uses BFS, but it deals with transforming one word into another instead of genetic sequences. LeetCode 126, word ladder 2, is a variation of this that requires you to find all shortest transformation sequences, which adds complexity. Then there's LeetCode 752, open the lock, which involves finding the minimum number of transformations to unlock a combination lock while avoiding dead-ends. And, of course, LeetCode 433, minimum genetic mutation, is the exact problem we're focusing on here. These problems share the core concept of BFS-based transformations and are great exercises to deepen your understanding of this graph traversal technique. Finally, let's briefly touch on some alternative approaches. One option is bidirectional BFS, which reduces the search space by starting the search simultaneously from both the start and end sequences. While this can be faster than regular BFS, it's more complex to implement and requires careful handling of the two search fronts. Another approach is A** search, which incorporates heuristic optimization. For example, you could use the Hamming distance as a heuristic to prioritize nodes closer to the target. However, designing an effective heuristic function can be challenging. Lastly, there's DFS, which is generally inefficient for this problem. It may find a solution, but it doesn't guarantee the shortest path. DFS should only be used if the problem explicitly requires generating all possible solutions rather than the optimal one. These alternatives are worth exploring, but BFS remains the most straightforward and reliable choice for this particular problem. Great job reaching the end of this problem walkthrough. To summarize, we tackled the minimum genetic mutation problem using BFS to calculate the shortest path in terms of valid sequence transformations. Remember, BFS is a go-to approach for unweighted graph problems, and understanding constraints is key. Thanks for watching, and don't forget to like and subscribe for more coding content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!